Recording in
Hello,
progress.
everyone. Welcome to our lecture that continues our conversation about expressions of concentration. We are going to take what we learned in our last discussion about novel or new concentration units and their different definitions, and see if we can't find a means to convert from one concentration unit to another. So when we're asking ourselves, like, how would I even begin this process of converting from one concentration unit to another? The answer lies with the concepts that we described when we looked at concentration in molarity and the density of a solution. Because in our discussion of molarity and density, we reminded ourselves that both of these properties of solutions are intensive properties. So a reminder as to what that means. An intensive property means it is the same or constant regardless of the quantity of the substance. So for example, if we're thinking specifically about molarity or density of a solution, I could give you, let's call this 100 milliliters of a 1.0 molar solution. And then if I were to pour some of this out into a smaller vessel that was maybe only 30 milliliters, the concentration in the smaller vessel would be the same, right? It's still the same proportion of solute to liters of solution. So the concentration is unchanged. Same molarity. Similar concept can be thought of for density. Let's use a solid, even though we've been talking about solutions, just so we have kind of a way to apply this to multiple different types of substances. So let's say that I've got this, I don't know, cube of metal here, and I know that its density is 9.28 grams per mil. If I were to cut out a little section of that cube, so this little guy, this little section of our cube would have the same density, right? Even though the amount of substance is smaller, we still have that same ratio of mass to volume. So we would have the same density. So why is this something that's important for us to know when thinking about converting between concentration units? So because all concentration units and solution density are intensive, we can select some quantity of solution and obtain some extensive properties in that quantity. So these would be things that do depend on how much you have. So this would be things like maybe moles of solutes, moles of solvent, mass of solution, etc. So these would be examples of some extensive properties that we could determine from some like selected chosen quantity of solution. And then once we have the required extensive properties, we can then make a proportion of our desired quantities, depending on what kind of concentration unit we're looking for. And that now becomes an intensive property that we can call a concentration unit. So it all depends on what kind of concentration unit we're talking about, what proportions or things are being related, what kind of extensive properties are being related in that concentration unit, and how I can maybe get an example of some quantity of those extensive units in a chosen sample of solution, which I can then make a ratio of to get a concentration. So for example, like I could say, oh, let's suppose I have 100 milliliters of solution. I would choose that value because that probably would make my life easy in terms of like figuring out things like moles or mass. But the idea is, even if I have the quantities of moles or mass or volume in that 100 mils, then once I get my ratio of the things I want, depending on the concentration unit, then that will be the same concentration found in the 30 mils or the 1 liter. So let's see if we can maybe practice this. So apologize in advance. This should say concentration. I tried to fix it. It's not perfect. It is what it is. So here we have an example of a really common way of expressing saline solution. So we've got some like made for animals, IV bag of saline. They've given us the volume in the bag. We'll see if that's the volume that we want. And we are asked to determine what is the concentration of a known concentration unit of saline in a particular unit. So let's see here. The unit that we want in this example is molarity. So our goal is to convert from a mass volume percent or a weight volume percent to molarity. So let's see if we can't figure out maybe some extensive properties. I think a good idea is perhaps starting from some definitions here. So if we're trying to convert from mass volume percent, remember the definition of mass volume percent is grams solute per volume solution. Here, milliliter solution times 100%. So we're going to ask ourselves, from our given mass volume percent, can we determine grams solute and then milliliters of solution? So this is where we need to make a choice. So we need to choose our quantity of solution so that we can obtain these extensive properties of mass and volume. So since we're talking about something real, right? Like we're talking about an actual IV bag whose volume was told to us, let's go ahead and assume like we've got one bag in front of us. So we're just going to assume we're looking at one IV bag, which contains, according to the label, 1,000 milliliters of solution. So since we have decided that we are going to stick with 1,000 milliliters of solution, we need to ensure that the grams of solute and mil solution and then all the stuff we're trying to get from that information is relative to this 1,000 mil sample we're talking about here. Okay, now before we start doing the actual calculations, let's remind ourselves about what is it that we're trying to get beyond just the components of the definition of a mass volume percent. We are trying here to find the molarity, which is moles of solutes over liters of solution. So these are the components that we are ultimately going to need to find so that we can get a proportion of them, which will then give us molarity. So let's see if we can't make some connections here. So we've started with this assumption. We're not going to abandon it. We've assumed that we had a bag of our IV solution, and that bag on the label says that contains 1,000 milliliters of saline. So because I've assumed that I have one bag of my saline solution, I now have something that relates volume solution, which is a term that I need in my molarity. The only issue is here I have my volume of solution in mils, whereas up here I need my volume of solution in liters. So I'm going to do a quick conversion. So converting milliliters to liters, if I've got 1,000 milliliters, by definition, I have 1.0 liter of solution. So awesome. I have half of my needed information to get my molarity. I now have my denominator. And now that I've got my denominator, I need to ask ask myself, ask us to figure out how can we get moles of NaCl needed. So let's think about what we assumed. We assumed that we had 1,000 mils of solution. So I'm just going to write that down. We had 1,000. I'm going to back up a little bit. 1,000 milliliters of solution. And then I am going to look at my given concentration, which was my mass volume percent. So mass volume percent. This says that if I were to have like 100 milliliters of solution, 0.9 grams would be present. So we can think about like, what is it that 0.9 weight per volume means? So this means that there's 0.90 grams per 1 mil of solution times 100. That is the definition of mass per volume percent. So then let's see how I can maybe use that to my advantage. All right, what do I want to cancel here? I want to cancel my milliliters. And I also am thinking that this percent, this 100% sticking around is not maybe so useful to us. So let's express this as a fraction. So 0.9 gram per mil percent is 0.90 grams, and then per mil, and then divide by 100. So we're just kind of like making it a decimal instead of a percentage. So that would move our decimal over 2 places. So 12.009 grams per 1 mil of solution. All right, mils of solution cancels. And I have dropped some important information. When you're doing these conversions, I strongly suggest that you identify solute solvent. So I'm going to say this is grams of our solute, which is sodium chloride here. And now let's look at what we're trying to find. We want the moles of sodium chloride. So far, I've taken my presumed 1,000 milliliter of solution, and I've used my definition of a mass volume percent to figure out the mass of sodium chloride present. So I need to look for information that allows me to perhaps convert my mass of sodium chloride into moles of sodium chloride. And if you look here in the problem, the molar mass of sodium chloride is 58.44 grams per mole. So I want to be left with moles of sodium chloride, and the molar mass says that 1 mole of sodium chloride weighs 58.44 grams. So we need to find this by taking 1,000, multiplying it by 0.009. That's really just moving our decimal over 3 places, and then dividing by 58.44. So 9 over 58.44. I get 0.154 with 2 zeros following. So that's nice for our sig figs. Moles of NaCl. And now I have my moles of solute, which means I can get my molarity. So my molarity is moles of NaCl per liter of my saline solution. So because I assumed I had 1,000 mils, this is going to be my 0.15400 moles NaCl over my liters of solution, which, because this bag was so nice and gave us 1,000 mils, that was 1 liter. So I can say over 1.0 liter. So we don't really have to do any math here because we're taking a number and dividing it by 1. This gives us a molarity of 0.154 molar NaCl. So this is our molarity of our solution, which is an intensive property that we obtained by solving for extensive property mole and volume, and then obtaining the proportion of those two. So this is going to be the method we employ when we do other concentration conversions in the future. So in our next video, we will explore this same kind of problem, still looking at this saline bag. But what if we don't want to convert to molarity, right? Because we're pretty familiar with molarity at this point. What if we want to convert to something different, like molality or parts per unit or a mole fraction? So these are the things that we'll be practicing in our next couple of videos. So I'll see you in the next one.